Long horizon manipulation training still faces two practical challenges. First, dense rewards are often used to guide exploration, but they can also be overexploited. A policy may achieve high return by repeatedly collecting shaping rewards while delaying or even failing to complete the task. Existing solutions can help, but they require extra tuning. Step costs need carefully chosen penalty weights, and dense to sparse schedules require task-specific switch times. Reward overexploitation also affects behavior quality. Even when the policy succeeds, it may take inefficient paths or produce unnecessary motion. In real-world transfer, this can lead to longer execution time, higher energy use, and less stable and less safe robot behavior. Second, rare early successes can be difficult to preserve. Early in training, the policy may discover an effective motion that completes the task. However, after policy updates, distribution shift can move the policy away from the states and actions that produce the success. As a result, a successful strategy may fail to become reliable behavior. To address these challenges, we propose Temporal Self-Imitation Learning, a reinforcement learning framework that turns self-generated successful trajectories into reusable supervision. During training, the agent first learns from the environment reward, with the temporal target set to the maximum episode horizon. Once the policy achieves a success, the trajectory is stored in fast success memory. In the next training iteration, the agent first recaps this memory, which provides two types of supervision. First, the completion time of the stored trajectory becomes an adaptive temporal target. The current policy is encouraged to finish before this target, which reduces reward overexploitation and improves behavioral efficiency. Second, the stored trajectory preserves efficient actions that the policy has already discovered. By replaying and imitating these actions, the policy is less likely to forget useful behavior during training. When the policy achieves an even faster success under the new temporal target, that trajectory updates the fast success memory. As a result, both the temporal target and the behavior used for imitation are improved for the next iteration. Together, these two signals help the policy optimize for efficient task completion, while reducing the need to rediscover rare successful behaviors from scratch. We evaluate temporal self-imitation learning, or TSIL, on 15 long-horizon manipulation tasks. TSIL achieves the best success rate and sample efficiency among the compared methods. It also completes more episodes within the same training budget and learns more efficient behaviors. We further visualize the learned behaviors. Compared with a fixed temporal target, TSIL produces cleaner and more direct executions. The policy completes the task with shorter and more purposeful behavior, showing that the adaptive temporal target improves both task success and motion quality. Temporal self-imitation learning also remains stable under challenging training settings, including very noisy policy gradients, aggressive dense reward dropout, larger policy updates, and high learning rates. These results show that TSIL is robust across difficult training conditions. Finally, we analyze two mechanisms behind these improvements. First, we examine how adaptive temporal targets change the training signal. The x-axis is normalized interaction time, where moving left means faster episodes, and the y-axis is normalized task return. Cell color shows empirical success rate, while the bright overlay shows where optimization assigns positive advantage mass. Adaptive temporal targets shift this update pressure toward fast successful trajectories, while reducing pressure on slow failures or reward-distracted behavior. In other words, the policy learns not only how to succeed, but which successes are temporally efficient. Second, we visualize how fast success replay preserves efficient behaviors after they are discovered. The background shows how likely nearby policies are to reproduce replay actions from fast success memory, with brighter regions indicating higher likelihood. The arrows show the policy update direction. Both self-imitation methods pull the policy towards stored successful behavior, but TSIL aligns the update more strongly with the bright, fast success regions. This suggests that TSIL does not simply replay high-return experience, it specifically revisits and reinforces the fastest successful behaviors. For more details, please refer to our paper and project website. Thank you.